Welcome to the Syntax Evolution, presented by Royal Research. This single glowing line surging forward represents an active execution thread. JavaScript operates in a strictly single-threaded, synchronous environment. The engine executes tasks one after another, in a fixed, linear sequence. In this linear model, network latency becomes a severe architectural bottleneck. Fetching data from a remote server or reading large files takes time. And in a synchronous system, the execution engine must stop and wait for that data to arrive. Looking at this timeline chart, the main thread runs horizontally. When a massive network request drops onto the line, forward processing halts. While waiting for the server, the interface freezes. Clicks are ignored and no other code executes until the request concludes. To prevent the interface from locking up, software engineers rely on asynchronous operations. Asynchronous execution delegates time-consuming tasks to the background. By moving network requests and file reads off the planary timeline, the main thread continues processing user interactions without interruption. Today, we are tracing the architectural evolution of how JavaScript manages these background tasks. We will track the progression from primitive callbacks to the structured promise state machine, and finally to modern async await syntax. Mastering this progression is a requirement for architecting software that remains responsive under heavy data loads. Consider a restaurant waiter to visualize how background delegation works. A waiter takes your order and hands it off to the kitchen. Instead of standing idle while the food cooks, the waiter continues serving other tables. This flowchart maps that analogy to JavaScript's architecture. On the left, the waiter represents the main thread, maintaining continuous activity. On the right, the chef represents a background API handling a long-running preparation task. Once complete, the system reconnects. The chef returns the meal to the waiter. This return trip is the callback. Historically, JavaScript developers implemented this using the callback pattern. You pass a function into another function, with instructions that the inner function should only execute after the initial background operation finishes. Here is a standard fetch implementation using setTimeout. The 2000 millisecond delay simulates network latency, queuing the callback to run when the timer expires. Meanwhile, the main thread skips the delay block and continues executing further down the file, keeping the application active. This system succeeds for single tasks, but it presents challenges when an application requires multiple sequential background operations. When sequencing dependent tasks, developers must nest callbacks inside other callbacks. This creates a cascading, right-leaning triangle known as callback hell. The actual business logic becomes buried under the nested dependency structure, making the code difficult to read and maintain. Because each callback handles its isolated scope, implementing comprehensive error handling across the sequence requires writing redundant logic at every single level. Callbacks proved the engine could successfully offload tasks, but their structural limitations forced a redesign to build more maintainable applications. The architectural solution to the callback scaling problem is the promise object. Structurally, a promise is an object that acts as a placeholder. It represents the eventual completion or failure of an asynchronous operation. We can see the mechanics in this state machine widget.
A promise operates under strict rules governed by three immutable states: pending, fulfilled, and rejected. When constructing a promise, the system provides resolve and reject functions to control the transitions. While actively gathering data, the machine remains in the pending state. If successful, it transitions to fulfilled, and data routes out of the promise block. This fulfilled state automatically triggers the then method, processing data sequentially outside the original scope. Conversely, if the network request fails, the machine immediately shifts to the rejected state. A rejection entirely bypasses any then logic. The error routes straight into a separate .catch method, isolating the error handling mechanism. Instead of nesting functions inward, promises chain methods downward. This flattens the execution flow, making sequential tasks read top to bottom rather than as a cascading triangle. Promises established a predictable pipeline for managing data that arrives out of order, providing the structural consistency missing from primitive callbacks. The ES 2017 standard introduced the final evolution in handling non-blocking execution, async await. This new syntax does not replace promises. It is a syntactic layer built directly on top of the exact same promise architecture we just examined. Watch this transformation. The chained .then methods morph directly into a modern async function declaration, visually stripping away the explicit promise chains. Inside this function, the await keyword dictates the execution flow. When the engine hits await, it pauses execution of this specific function until the internal promise resolves, leaving the main thread free. This achieves a major engineering goal. It allows asynchronous, non-blocking operations to be written and read top to bottom, exactly like standard synchronous code. Because the code reads sequentially, developers remove .catch methods entirely. Instead, they manage failures by wrapping the await logic in standard try-catch blocks. Sequential syntax is highly readable, but optimizing performance requires running multiple independent network requests simultaneously, rather than one after the other. The promise.all method handles this concurrency requirement. This split timeline illustrates two API fetches executing on parallel background tracks simultaneously. The execution thread waits for both to resolve, consolidating the combined results into a single array variable. Async await, combined with concurrent execution methods, allows developers to write readable applications that still leverage parallel background processing. These architectural paradigms form the backbone of modern engineering environments. These three code modules show where this module is mandatory: gathering front-end data via browser APIs, reading server files on Node, and processing parallel streams. Despite different contexts, all three rely on the underlying promise architecture to prevent the main thread from locking up. The evolution from nested callbacks to the synchronous-looking syntax of async await has changed how developers handle the timing of data retrieval. Delegating and managing non-blocking execution is the foundational requirement for building applications that remain responsive under heavy loads. Implementing these patterns effectively ensures that user interfaces remain fluid, regardless of the amount of background processing required. Thank you for following Insight Engine by Royal Research.